So after a long time, today we'll be discussing about a class on binary trees. So first we'll deal about what a tree is basically. So tree is a one which is representing the nodes and connected by edges. So what are nodes and what are edges? So here in the diagram you can see that A, B, C, D, E, F, G so on up to J has been displayed in circles. So these are the nodes. So these are called the nodes and the line representation is called the edges. So both together constitute the nodes and the edges. So in this session we'll be discussing about binary tree or binary search tree specifically. So putting it into a definition, binary tree is a special data structure used for data storage purposes. So a binary tree is a data structure which is used for the storage of memory. A binary tree has a special condition that each node can have maximum of 2 children. So as you can see in the picture itself, A has two of the child nodes, that is B and C, and as you can see only two of the nodes are present. These are the maximum number of nodes any of the parent node can have. So therefore a binary tree can also be called to have a special condition that each node can have maximum of only 2 children. A binary tree has the benefits of both an ordered array and a linked list, as search is as quick as a sorted array and insertion or deletion of operation is as fast as linked list. So the benefit or the advantage of using a binary tree is, as you can see in ordered array, you can use the linked list for searching any of the element quickly in a binary tree, as well as in a sorted array you can also put an element, that is insertion, or delete an element from the node in the binary tree itself. So you can see this advantage in a binary tree. So as we move further you will see, I'll explain it prior itself. A here is the level 0, B and C has been given the level 1 because they are the first child nodes that have been created by node A, that is the parent node. Then level 2 comprises of D, E, F, G, and level 3 at the last is H, I and J. So as we proceed further, you'll see that we come across the terms called subtree, leaf node, parent node, child node, root, etc. and also siblings. So these are the some of the important terms you need to remember when you deal with the topic binary trees. So path. Path refers to the sequence of nodes along the edges of a tree. So path is basically representing the direction of the node. So it acts along the edges of a tree. So root. The node at the top of the tree is called a root. So the topmost node is normally called the root. So in the previous example you can see in the previous picture, A is called the root. Parent. Any node except the root node has one edge upward to a node, and that is called a parent. So any node except the root node has one edge upward to a node. So basically they have told in the definition is that any node, suppose we take the example B, so this has an upward node. So A is the parent of this node. So apart from the root, as well as it is a parent node as well as its root node also, so A is an exception. So if we take for B, then D has an upward node, therefore B is a parent node. And if I also have an upward node, that is here you can see there is, so D is the parent node. So they have put into simple terms. Now we look into what a child node is. A node below a given node connected by its edge downward is called a child node. It's simple as you can see in the picture. Leaf. The node which does not have any child node is called a leaf node. So here you can see that F does not have any node downwards it. Therefore it can be termed to be a leaf node. Subtree. Subtree represents the descendants of a node. So here you can see that D, H and I have been marked as in a triangle. So you can mark this as a subtree because these are the descendants of the tree, that is they form a family over here, so they can be termed as a subtree. Visiting. Visiting refers to checking the value of a node when control is on the node. So what does visiting means? Visiting is to check the value at the present at the node. So as you can see, whenever I'll take the example of a pointer. So whenever a pointer points to a memory, then you can see the value at that particular point. Similarly, using the visitor, you can refer to checking the value of a node when control is at that particular node. Traversing is common everywhere. It means passing through nodes in a specific direction or order. Levels. Level of a node represents the generation of a node. If the root node is at level 0, then its next child node is level 1, its grandchild is at level 2 and so on. So here you can see the level 0, level 1, level 2 and level 3. Now keys. Keys represent a value of a node based on which a search operation is to be carried out for a node. So key is a value which is normally taken so as we can use that value to search a particular node in the binary tree. So now we move on to know how is the representation of a binary search tree done. So a binary search tree has a special behavior, that is a node's left child must always have a value less than its parent value and the node's right child must have a value greater than its parent value. So we'll understand this from the diagram. So here itself you can see this is the parent node. So towards its left the value is 14, which is of course less than 27, and towards its right you can see the value is 35, which is greater than 27. So in the subtree itself you can see here, now onwards I will be using the terms so that you can memorize it as well. So here in this left subtree you can see that 10, which is at the left side of 14, is less than 14 and 19 is greater than 14 towards its right. Similarly for the right subtree. Now we move forward to see what is a tree node. The code to write a tree node would be similar to what is given below. So we'll see how the basic representation of a tree node is done using the structure. So a tree node has two parts in it. One is the data part and the second is its references. So inside the references you can divide it into subparts, that is left and right child node. So this is a basic representation of how a structured node has. So struct node int data, struct node star left child, struct node star right child. So these are pointers to the child nodes of the binary tree. In a tree, all nodes share a common construct. In a tree, that is all of the nodes share the same memory location. Now we look on into the basic operations that are performed on a binary search tree. That is, the basic operation that can be performed on a binary search tree data structures are insert, search, pre-order traversal, in-order traversal, post-order traversal. So what is insert? Insert is basically, as its term suggests, is an inserting an element in a tree or create a tree. Search is used to search an element in a tree. Pre-order traversal means to traverse a tree in a pre-order manner. So in the further slides ahead we'll be discussing what does the term pre-order, in-order and post-order mean. So I'll cover up the next two terms also. So in-order traversal means to traverse a tree in an in-order manner, and post-order traversal means to traverse a tree in a post-order manner. So now we'll look on into what does these terms mean. So first we'll look on into how insertion operation is done on a binary search tree. So the very first operation is insertion, that is to create the tree. Afterwards, after creation, whenever an element is to be inserted, first locate its proper location. Start searching from the root node. So whenever you need to insert an element into the binary search tree, you need to first locate its proper location. For that, we'll be using the keyword as you have seen in the previous slides. So we'll further read what does it state. So start searching from the root node. Then if the data is less than a key value, search for the empty location in the left subtree and insert the data. Note here that whenever you find an empty location, then only you can insert the data. So that's the reason why we'll read the second statement once again. Start searching from the root node. Then if the data is less than the key value, search for the empty location in the left subtree and insert the data. Otherwise, search for the empty location in the right subtree and insert the data. I hope I'm very clear about this. I'll repeat it once again that whenever you find an empty location, that's the point you can do your insertion of element. Now we move on further into see what is the algorithm. If root is null, then create root node return. So this is simple. You find an empty location, you store, you create a element, you insert an element. In fact, then if root exists, then compare the data with the node dot data while until insertion position is located. This is the while condition. Then if data is greater than the node dot data, go to right subtree. That is, if the data is greater than, because you know that at the right side always the value is greater than the parent node. So if the data is greater than the node dot data, go to right subtree, else go to left subtree, then end of the while loop, end of the while condition, and then we'll insert the data and we'll close end if. That's basic. So this is a basic implementation of a insert function. So this is how it looks like. So void insert function in data as its argument, data has been taken as its argument. Struct node, start temp node, we allocate the memory dynamically. So struct node malloc size of struct node, then we take two of the pointers, that is current and parent. So temp node points to data equal to data, temp node points to left child equal to null, temp node points to right child equal to null. So we have pointed the left and the right child as null. So if the tree is empty beforehand, create root node. So if root is double equal to null, then make it as a temp node, else condition the current is equal to root, and we store null in the place of parent. So until the condition becomes false, while condition parent equal to current, go to the left of the tree. That is, in order to go to the left part of the tree, if data is less than the parent points to data, this means that if the value of the value at the left node is less than the value at the parent node, then we insert the value, that is current equal to current points to left child, and insert to the left, that is if current double equal to null, then parent points to left child equal to temp node return. So this is done to insert the value into the left, and this is done to move the current key value towards the left of the tree. Similarly, as we have done in the left side, we'll do it in the right side as well. That is else current equal to current points to right child. Now the insertion part, if current double equal to null, if you find an empty location, then parent points to right child, temp node's value stored in the right child node return. That's it. Now we move further to see the algorithm as well as the implementation of a search operation. So what is a search operation? Whenever an element is to be searched, start searching from the root node, that is the topmost node. Then if the data is less than the key value, search for the element in the left subtree. Otherwise, search for the element in the right subtree. So if you find the data is less than the key value, then you need to first move on to the left subnode, that is left side of the binary tree, or else if you find it greater, then you must move to the right side of the subtree. So we'll see the algorithm first. If root.data is equal to search.data, return root. So if you find the root.data is equal to the search.data, so what you're searching for and the parent node, that is the topmost node, are same, then you will directly represent or you will directly show the root, that is a topmost node. Else condition, until the data is found, the condition follows. If data is greater than the node.data, go to right subtree. That is, if the data you find is greater than the parent node's data, you go to the right subtree, else to the left subtree, else condition. If data is found, return node and end while. If it's not found, you close the condition, that is end 0. So end if condition. Now we'll see basically what the implementation of algorithm. So here you can see struct node star search in data, struct node star current equal to root, printf visiting elements. So here we'll be doing the visiting so as to visit the elements to search for that particular node. So while current points to data not equal to data, that is current, the node which is there particularly at with a data value, if it's not equal to the data value, then only the loop will run. So if current not equal to null, so if it's not equal to null, if it's empty, if it's not an empty location, then printf current points to data. Now in order to move to the left side, left subtree, if current points to data is greater than data, so this is the parent node's value, and if its value is greater, then we move on to the left child. So current equal to current points to left child, else go to the right tree, that is current equal to current points to right child. If not found, current double equal to null and return null's value, return current. Now we move forward to see what a traversal means. Traversal is a process to visit all the nodes of a tree and may print the values too. Because all nodes are connected via edges, links, we always start from the root, that is the topmost node. This is why we cannot randomly access a node in a tree directly. So there are three ways to use traversal in a binary search tree. These are in order, pre-order and post-order traversal. Generally, we traverse a tree to search, locate a given item or key in the tree, or to print all the values it contains. The first kind of traversal is in-order traversal. In this traversal method, the left subtree is visited first, then the root, and later the right subtree. So there's a sequence of visiting in the in-order traversal. First we move on to the left subtree, then the root, then the right subtree. So we should always remember that every node may represent a subtree itself. So if a binary tree is traversed in order, the output will produce sorted key values in a ascending order. So this is the representation. So how is it done? 1 2 3, then 2, then inside 3 1 2 3. So first left, then root, then right subtree. So we start from A and following in order traversal, we move to its left subtree, that is B. B is also traversed in order. The process goes on until all the nodes are visited. So these are the output, that is D, B, E, A, F, C, G. D, B, E, A, F, C, G. Left to right. So yeah. Until all nodes are traversed, step 1, recursively traverse left subtree. Step 2, visit root node. Step 3, recursively traverse right subtree. Now the process of pre-order traversal. In this traversal method, the root node is first visited, then the left, and finally the right. So here you can see the representation 1, 1, 2, 3, 1, 2, 3. So A, B, D, E, C, F, G. A, B, D, E, C, F, G. We start from A and following pre-order traversal, we first visit A itself, that is the topmost node itself, and then move to the left subtree, that is B. B is also traversed pre-order, that is from the parent node of the subtree itself. The process goes on until all the nodes are visited. The output of pre-order traversal is shown here. So algorithm is same, that is visit the root node, recursively traverse left subtree, recursively traverse right subtree. Now we move on to the last method of traversal, that is the post-order traversal. So in this traversal method, the root node is visited last, hence the name. First we traverse the left subtree, then the right subtree, and finally the root subtree. So 1 2 3, 1 2 3, and at the last the root node. So we'll see the order, that is D E B F, G, C and A. So here the topmost node, that is the root node, is visited at last. That's the name post order traversal. We start from A and following post order traversal we first visit the left subtree B. B is also traversed post order and hence the process go on until all the nodes are visited. The output of the post order traversal of this tree will be D, E, B, F, G, C, A. Algorithm: until all nodes are traversed, recursively traverse left subtree. Step 2. Recursively traverse right subtree. Step 3. Visit root node. So for all these three methods, the algorithm is very important along with the output you need to write whenever asked in assignment or as a question. So once again we'll see a binary search trees methods and its value, why is it important. A binary search tree is a tree in which all the nodes follow the below mentioned properties. The value of the key of the left subtree is less than the value of its parent node's key. The value of the key of the right subtree is greater than or equal to its value of its parent node key. As we have discussed, we'll revise once again. So here left subtree keys, that is the key here, is less than the node, that is the root node, is less than or equal to right subtree value. And this is the basic representation. We'll revise again. It's a collection of nodes arranged in a way where they can maintain BST properties. Each node has a key and an associated value, that is the left and the right node. While searching, the desired key is compared to the keys in BST and if found, the associated value is retrieved. So this was the representation. Here we observe that the root node key 27 has all less valued keys on the left subtree and the higher valued on the right subtree. So there are types of binary tree as well. So one of them is full binary tree. A binary tree is a full binary tree if every node has 0 or 2 children. So here you can see that here every node has 0 at least 2 children. So that's why this is a perfect example of a full binary tree. The following are the example of a full binary tree. We can also say a full binary tree is a binary tree in which all nodes except the leaf nodes have 2 children. In a full binary tree, number of leaf node is the number of internal nodes plus 1. So remember this formula is very important whenever asked as a 1 mark or 2 mark numerical. So L equal to I plus 1, where L is number of leaf node and I equal to number of internal node. Complete binary tree. A binary tree is a complete binary tree if all the levels are completely filled except possibly the last level or the lowest level has all keys as left as possible. So here you can see in this condition it has lowest level does not have any of the filled nodes. So this can be called as a complete example of a binary heap or a complete binary tree as well. So here you can see it has also been referred as practical example of binary heap. Now the perfect binary tree. A binary tree is said to be perfect in which all the internal nodes have 2 children and all the leaf nodes are at the same level as well. So if all the leaf node that is are at this level 3 itself and even the internal nodes are at level 3 and it has all the child node also, then it can be termed as a perfect binary tree. A perfect binary tree of height h, where height is the number of nodes on the path from the root to the leaf, has 2 power h minus 1. So a perfect binary tree of height h, h is the number of level or number of nodes covered whenever it reaches from the root to the particular leaf, then its formula is 2 power h minus 1. Even note this formula as well. An example of a perfect binary tree is ancestors and family. Yes. Now we move further to see extended binary tree. Extended binary tree is a type of a binary tree in which all the null subtree of the original tree are replaced with special node called external node, whereas other nodes are called internal node. So extended binary tree does not have any null nodes, null subtree. So all this null value subtree are replaced with a external node and all the others other than the null is replaced with internal nodes. So together the external and the internal node comprise the whole concept of extended binary tree. Here the circles represent the internal node. These 1, 2, 3, 4, 5 are the internal node, and the boxes here, that is the null value they had because they have been replaced now with the external node, are called the external node. Now we look on into the properties of external binary tree. The nodes from the original tree are internal nodes and the special nodes are called external nodes. All external nodes are leaf node and the internal nodes are non-leaf nodes. Every internal node has exactly two children and every external node is a leaf. It displays the result which is a complete binary tree. So this is a property of an external binary tree. So these three properties are very important. Now we'll see into a program which makes use of an extended binary tree. So a tree node struct node int key the data value. Thus we have created struct node star pointers, that is left and right. Now the utility function to create a new node, that is node star new node int key node star temp equal to new node. The value of new node has been saved into temp. Temp points to key equal to key. So it points to the key value inside its whole memory. Then temp points to left equal to temp points to right equal to null. So it has been declared with a null value, the pointer. We return the temp value. Now the function for in-order traversal, void traverse node star root. If root not equal to null, traverse root points to left, cout root points to key, traverse root points to right. So here you can see that traversal has been done here. So if the root's value is not equal to null, as long as the topmost node root's value is not equal to null, traverse root points to left, cout root points to key. Here you can see that traversal is first done towards the left, then the key value is printed. After printing the left value, we move on to traverse the right value here. Traverse root points to right. Then after that else condition, making the external nodes. So root equal to new node minus 1. Then after that we'll be displaying the data value at a particular node after creating the new node, that is root points to key, and hence we provide spaces to have a better look. Now we move on to the further driver code inside the main function, that is node star root equal to new node. We have created a new node 1, root points to left, that is we have assigned the new node at the left side to be 2, towards the right as 3, and towards the grandchild of the parent, that is root points to left as the value 5, and root points to right. These both are the grandchild in the binary search tree equal to new node 4, and at last we will be calling the function traverse root return 0. So this would be the output. You can once verify with running your program at your computer. Now we move further to see what is a basic application of an extended binary tree. So how is calculation of a weighted path length done? So calculation of a weighted path length is done using the formula, that is P total path length is equal to the number of edges into the number of nodes. That is, here you can see the sum of total weight is already calculated and stored in the external node, and thus it makes it very much easy to calculate the total path length of a tree with a given weight. The same technique can also be used to update routing tables in a network. So we can also convert any of the binary tree into complete binary tree, but it requires a process, and the process is that the above given tree having removed all the external node is not a complete binary tree. So in order to introduce any tree as a complete binary tree, external nodes are added into it. That is, all the null values are replaced and external nodes are added to it. And thus a heap is a great example of a complete binary tree, and thus each binary tree can be expressed as heap if external nodes are added to it. Thank you.